Welcome back, folks. My name is Aaron Dolan, and this is our fifth lecture in our journey exploring electrical engineering principles. I'd like to start out today by going on a journey to a movie theater. Okay, we're not going to the movies. We're going to the parking lot. We're going to the parking lot right next to the movie theater, and we're going to look at these power lines. Many of you have already been there. You've stood underneath these power lines. You've heard the 60 hertz hum, and you may have even heard the crackling of electricity. Some of you have even been to the source of these power lines, and that's another amazing technology. What I'd like to draw your attention to is the fact that the power lines always come in groups of threes. You can see the three large insulators here, and you can see the pairing of wires. So these two are at the same electrical potential. We'll call that phase A. These two are at the same electrical potential, phase B. And finally, we have phase C over here. We can describe that three-phase system using three electrical generators. These are alternating current generators. And just so we're consistent, I'm going to add a plus here, negative there, and a plus there. Then we're going to show the exiting wires. And we'll call this phase A. We'll call this phase B. We'll call this phase C. At some point in the near future, I'm going to ask you to calculate the voltage A with respect to B. And when we get there, your response is going to be the same as the response you would have given today. You would say, well, muscle memory says I start in the lower left-hand corner and I walk up. And as I go along, I record the voltages. So I would say that this is voltage B to N. I'm going to put an N here. We're going to call that a neutral. Minus, because right now we're walking into a negative terminal of a power supply, minus Vn to A plus voltage A with respect to B is equal to 0. What we've just done is we have used Kirchhoff's voltage law. That's one of the very important tools in our toolkit. KVL. You see it again and again and again. And it's the topic of today's lecture. And that lecture is mesh and nodal analysis. Before we get started, let's do a quick review. So we had Kirchhoff's voltage law. And it told us that in a closed loop, the sum of the voltages equals 0. We had a shorthand for that, which said the summation of the voltages on a closed loop is equal to 0. The typical example we worked looked like this, where we have a 9-volt battery and a 2-volt battery, a 14 ohm resistor. We can put the polarity markings here. So these batteries are connected up rather strangely in that the two terminals are connected to each other. But that's okay, because we start here in the lower left-hand corner, and we're going to travel around the circuit. We're going to go in a closed loop. We're going to write an equation. We start our journey at the negative terminal of the 9-volt battery. That gives us negative 9. We move here to the positive terminal of the 2-volt battery. So that's plus 2. Plus VR1 is equal to 0. We'll call this resistor 1. Solving for that, we say the voltage on R1 is 7 volts. And we could even go so far as to say the current, because if it's a series current and we're walking, we are the current, aren't we? Right, so we could say the current is a voltage divided by a resistance. which gives us 7 volts over 14 ohms, or 500 milliamps. Okay, so that's the type of thing we could do with Kirchhoff's voltage law. Kirchhoff's current law tells us that for a given node, the sum of the currents equals 0. Mathematically, we would say that the summation of the currents is equal to 0. Or as I like to say, the goes intos got to equals the goes outas. So the current in to a node must equal the current leaving that node. We worked examples such as this, where we said there was 10 amperes flowing in this direction, 5 amps flowing in that direction. And then we talked about other elements like this, so maybe element A. And you were asked to solve for the current on element A. And you would say that the summation of the current in is the summation of the current out. From this problem, you can see that there is 10 amps going in. We can say there's 5 amps going out. And by inspection, in order to keep this current here in that direction and positive, we're going to assume that that's an output. So you would say X is equal to 5 amps in this particular case. That's 5 amps flowing in that direction. So if we're sitting on this node right here, Kirchhoff's current law tells us that the summation of the currents in must equal the summation of the currents out. KVL and KCL are powerful tools. When you combine them with Ohm's law, plus your ability to manipulate the resistors in a circuit to simplify it, you can get a long ways in electronics. But you will reach a point where there are problems you cannot solve. That's where nodal and mesh come in. That's a good reason to study them. As a side note, I would argue that mesh and nodal are very important because they reinforce the concepts of KVL and KCL. For example, in this class, you probably feel like you're a week or two behind, right? You're able to do some of the problems, but maybe not understand them very well. Look at it this way. Nodal and mesh will give you some very concrete examples that will anchor KVL and KCL, and you'll come out the other side understanding them much, much better. With that said, let's start with mesh analysis. This is based on KVL. In particular, we are talking about the summation of voltages on a closed loop is equal to 0. We are going to study many, many loops. Something else you need to remember is Ohm's law. So voltage, current, resistance, and the voltage is a current times a resistance. These two facts, the fact that we are talking about loops and the fact that voltage can be expressed as the product of a current and a resistance, are critical to understanding mesh analysis. In truth, I've been setting you up for this for quite some time. We have a circuit like this. I've routinely told you to start in this corner, right, for muscle memory. So start in that corner and take a trip around the circuit. There's another way of saying take a trip around the circuit, and that is, in a series circuit, current is the same for all elements. We could talk about a current A flowing in this circuit. That's the same thing as saying take a trip around the circuit. Now, our loop equation, since we're starting on the negative terminal of this power supply, our first number is negative 10. Then we would say the voltage on R1 plus the voltage on R2 is equal to 0. So let's see. We did this piece where we said we walked around a loop. So we made a closed loop and we made an equation for that. Now we're going to go back and we're going to use this piece. And we're going to say that a voltage is actually a current times a resistance. That brings us to this. So negative 10. Now we could talk about the voltage on R1, but we said it's a current times a resistance. So this would be plus 5 is the resistance, current A, right? Because again, a voltage is a current times a resistance. Plus, the resistance here is 15, 15, and there's that current again, equals 0. And now we solve. And we say that 20 current A is equal to 10. So current A is equal to 1/2 of an amp, or more appropriately, we would say this is 500 milliamps. So we go back up here, and we can say that there's 500 milliamps flowing in that circuit. We can verify that using the tools that are already in our toolbox. We would have said a current is the source voltage divided by the total resistance, which is 10 divided by 5 in series with 15, so that's 20. So our current is 500 milliamps. Okay, so far it at least seems to be consistent with what we know. One more time, we talked about a loop. So we've had a closed loop where the voltages were equal to 0. And then we have the substitution, where we always wrote voltages in terms of a current multiplied by a resistance. Let's try something new. With the tools we have, this is a challenging problem. And the reason it's so challenging is because it's neither in series nor in parallel. In fact, there are 2 currents circulating in it, or at least that's one way you could look at it. You could talk about a current A and a current B. And this gets really tricky with that R3 because you've got one current flowing down. So current A would be flowing in the downward direction. Right, here's current A. And we have current B that relative to that resistor is flowing in the upwards direction. Hold that thought. We'll come back to it. Well, how do you solve this? The answer is always the same. Muscle memory. Start in the lower left-hand corner and take a walk. Entering the negative 10. So the first loop equation is negative 10 plus the voltage on R1. Except I don't want to write it that way. I want to write that as 2IA. Because we said a voltage, get our card here, we said a voltage could always be substituted as a resistance times a current. That brings us to resistor 3, and we will write that as 8 current A. Okay, that's going down, but there's also current B going up. So current A and B are in opposite directions, which implies that we can subtract off current B. And then we're back to the beginning of our loop, so that is equal to 0. If we simplify this, we end up with 10A minus 8B is equal to 0. You'll notice I'm dropping the current and then the subscript and just using the subscript. So effectively what I've done is I said, we're just going to call this A and we're going to call this B. I think it makes it a little bit easier as we go along. Less strokes to make with the pen, less mistakes to make. That took care of loop A. Now we do loop B. We do the same thing as before. We start in this corner, again muscle memory, and we make the loop. Okay, here we go. We would start as 8 current B minus 8 current A. Again, they're at cross purposes with each other. We are now here entering this power supply on a positive terminal. So that's plus 7 plus 3 current B is equal to 0. If we solve for that, we end up with 8A plus 11B is equal to negative 7. Uh-oh, we almost made a mistake here. If it's negative 10 on this side, it better cross over to the other side as positive 10. At this point, we have two equations and two unknowns. We can solve this using the calculator's simultaneous equation function. To get started, we write this in matrix form. And we just take these numbers and put them in columns and rows. So 10, negative 8, 10. And then our second equation is negative 8, 11, negative 7. We turn on the calculator, go to Mode, Equation. And we want this first one. So we have A and B as unknowns. We go 1. Now here is the matrix, and we need to enter that. So 10 equals negative 8 equals 10 equals negative 8, 11, negative 7. And then you hit equals. This is current A. So current A is approximately 1.17 amps. And current B is approximately, you find that by pushing equals, so that's the Y term in this particular case, is approximately 0.22 amps, or more properly, 220 milliamps. You could think of mesh analysis as an algorithm. So the steps are, we write a KVL equation for each loop. To simplify this process and to convert it into muscle memory, I would recommend you always start in the lower left corner. Always move in a clockwise direction. Consider resistors to be positive, where the voltage on each resistor is expressed as a resistance multiplied by a current. Once you have the loop equations, you simplify them, put them into matrix form, and then use a calculator or computer to solve it for you. Could you do this by hand? Yes, absolutely, but it's a lot of work. On the exams and quizzes, I will do one of two things. I will either ask you to solve it using your calculator, and I assume you have a calculator and are able to use it very quickly, or I may ask you simply to put it into these forms right here. I may say the words set up, but do not solve and do not simplify. And the important part of this is that you know how to work the loops. Okay, that's what I'm really after. However, there are some times when I ask you to calculate the voltage on something like this resistor, which will work in a moment. Let's work another example. Now that the circuit is drawn, let's add our loops. We'll let this be current A. We'll let this one be current B. And this, we'll let this be current C. And now we can do our loop equations. For loop A, starting in the lower left corner, we make a journey. We would encounter this resistor, so we'll call that 2A. Now we're on R3 plus 5A minus 5C, because current C is flowing against current A, which brings us here. We record that as plus 10 plus 4A minus 4B is equal to 0. Simplifying that, that works out to 11A minus 4B minus 5C is equal to negative 10. Next is loop B. So that we start here and work our way up. So that's 4B minus 4A. Again, current A and B are moving opposite each other. We're entering this power supply on that terminal, so that's negative 10 plus 2B minus 2C. Current B and C are moving against each other. Let's see what's next. That brings us to here. Plus 3B is equal to 0. Simplifying, that's negative 4A plus 9B minus 2C equals 10. And finally, the last loop, loop C. We start our journey here, moving that way. We record that as 3C, brings us to this power supply, plus 20. We're now here, and that's plus 2C minus 2B, which brings us to this point, plus 5C minus 5A, and all of that is equal to 0. Simplifying, let's see, there we go. Simplifying that, we end up with negative 5A minus 2B plus 10C equals negative 20. We have 3 equations and we have 3 unknowns. We now put it into matrix form. So it's 11, negative 4, negative 5, negative 10. So that's these terms right here. Here's the B loop, so negative 4, 9, negative 2, 10. And finally the C loop, so negative 5, negative 2, 10, negative 20. From there, you go to your calculator, setup, equation. This time we have 3 unknowns, so we're going to want to use number 2. And you enter the numbers. 11, negative 4, negative 5, negative 10, negative 4, 9, oops, that's not what I wanted. Go back up. Where were we? Negative 2, 10, and negative 20. Let's see, do we have that right? Let me take a close look here. So if you make a mistake, you can walk back into the table. So 11, negative 4, negative 5, negative 10, negative 4, 9, negative 2, 10, negative 5, negative 2, 10, negative 20. Okay, good. That first one is current A. So current A is approximately negative 2.95 amps. The next one is B. So current B is approximately negative 1.02. And finally, current C is approximately negative 3.68 amps. You'll notice that some of these numbers, actually all of them, are negative. What that means is when we establish this loop current flowing in that direction, it means the actual flow is in the opposite direction. And that's fine. Just keep that in mind. So if we wanted to talk about current A, it's actually in this direction at 2.95 amps. Right? If we need to, we can substitute that in later. No harm, no foul. Just remember, opposite direction. Some folks will try to predict which way the current is going to be, but I would advise against that. And the reason I advise against it is because you want this to be a muscle memory operation. You don't have to think about it. Make it an algorithm. Make it an algorithm where you're always starting in the lower left, always moving in a clockwise direction, always making these assumptions. And what will happen is the problems end up being solved very quickly, and you don't have to think when you're doing it. So you can think with your pencil, you think with muscle memory. And then when you get to this point, you can engage the brain and say, well, that must mean the current is flowing in the opposite direction from the assumption that I initially made. Let's go look at something a little more closely. Suppose you wanted to know the voltage. Okay, this is kind of an evil thing to ask, but let's say we wanted to know the voltage on R4. Could we solve that? And I think we can. So first, we come down here and we draw R4 by itself. And we said R4 was, what was it? It's 4 ohms. Okay, how convenient. So 4 ohms. And now we need to show what the currents are. Because remember, there's two currents. There's a current A and there's a current B, and they're moving in opposite directions. So we had current A flowing in this direction, and current A was negative 2.95 amps. Right? There's our current A, right? That's this loop here, flowing down. Current B is flowing up, and current B was negative 1.02 amps. I'm going to make a substitution. Let's redraw this. And I'm going to flip the current. I'm going to show that current A is flowing in that direction, and it's 2.95 amps. And I'm going to show that current B is flowing in this direction at 1.02 amps. Just getting rid of the negatives because it makes it a little easier to think your way through it. We can redraw this again. So here's our 4 ohm resistor. And if you looked at this, we would say this is 2.95 minus 1.02. So set up, put it back into normal mode. So 2.95 minus 1.02. So we would say there is a current flow of 1.93 amperes in that direction. If that's true, we can calculate the voltage on R4 as a current by resistance. So that's 1.93 by 4, which gives us 7.7 volts DC. If you want to be really fussy, we have to talk about whether that's a positive or a negative. So if we connected our voltmeter up this way with our red wire here, this is going to read negative 7.7 volts DC. As a thought experiment, consider this. If we had a power supply and I told you that the circuit was like this, you would tell me that the current is flowing in this direction. So if you had a voltmeter like so, with a positive wire there, you would say, okay, I'm measuring from the positive with the current flowing in, therefore I'm going to read a positive voltage. But that's not what we have here, is it? Instead, we have something similar to this. So I've flipped the current here, and you can see that now the current is flowing in this direction. Current is flowing in that direction. And our voltmeter, as connected up here, would read a negative. Okay, again, that's the case here. When we look at the current on A, we see that it's positive in that direction. So it's not this one, it's this one here. Our last topic for today is node voltage analysis. And this is based on Kirchhoff's current law. Remember your Ohm's law? There was something about a current being equal to a voltage divided by a resistance. And this is going to be a very important substitution for us. Let's work a quick example. So you have 5 amps and you have 2 resistors. For this example, we need to find the voltage that appears across each resistor. Now, we could certainly do this with the tools we have, but we're going to use something called node analysis. As we get started, I'm going to establish a reference node. So when we talk about voltages, we're going to make everything with respect to this node here, and we're going to call that ground. So if we were to talk about a voltmeter would be connected from there to ground. Here's how nodal analysis works. First, you establish where your nodes are. Pretty simple in this particular circuit because there's only two nodes. There's the ground node and then there's the voltage A node. Once we've established the node, we are going to sit on that node and we are going to do a calculation assuming that every wire that goes into that node has a current that is leaving. This is similar to our previous example where we always went in a clockwise loop. This time we're always going to assume that the current is leaving the node. That'll make sense why in a moment. So if this current is leaving, we would record this as negative 5 amps. So that takes care of this leg here. Now we go to the R1 and we assume that the current is leaving. So we would say that is voltage A over 2 ohms. That is current, right? We have a voltage over resistance. And we're assuming it's leaving the node. Next we do resistor 2. So we would call that voltage A divided by 5. And we set that equal to 0. This works because of Kirchhoff's current law. You remember the summations of currents on a node is equal to 0. We can solve this. It takes a little bit of math. So what we'll do is just for simplification, we'll multiply everything by 10. So this would be negative 50 plus 5a plus 2a is equal to 0. All right, we just want to get rid of these fractions real quick. Solving for that, 7a is equal to 50. So the voltage A is equal to 7.1 volts DC. Using the tools we had previously, we would have solved this problem, I don't know, you might have said that R total, so 1 over R total, is 1 over 2 plus 1 over 5. And you would have said 2 inverse plus 5 inverse equals inverse equals. So you would have then said that the voltage A is a current by a resistance. So voltage A is, 5 amps by 1.43. So we multiply this by 5, and we should get the same answer. So voltage A is about 7.1 volts DC. Okay, that was the tools we had, and this is our new tool using the nodal analysis. Let's work an example. How many nodes do you see? Well, I would argue that there's one there. There's a node there. There's a node there. And then we'll establish this. Actually, let's put it over here. We'll establish this as our reference node. So there are 4 nodes. Let this be voltage A with respect to ground. Let this be voltage B with respect to ground. And let this be voltage C with respect to ground. The voltage on node A is very easy. By inspection, we would say node A would say that A is just equals 7. Okay, that was easy. Node B, we've got 3 currents. Again, we're going to assume they are all leaving. This makes the math easier. For R1, we would say B, that's voltage B, minus voltage A, divided by 4. is the current leaving through R1. For R2, we have a current of B divided by 2. And for R3, we have B minus C divided by 4. And that's the current through R3. And finally, that's equal to 0. If we simplify that, it comes out to negative A plus 4B minus C is equal to 0. For node C, we have this current leaving and this current leaving. So that would be C minus B over 4 plus C divided by 2 is equal to 0. And simplifying that, we end up with negative B plus 3C is equal to 0. There's one equation, two equations, three equations with unknowns A, B, and C. Just like before, we can put that into matrix form. The first one's a little bit tricky, but we're going to say A, no B, no C is equal to 7. That's how you'd read that. A is equal to 7. Then you would put in the other numbers, negative 1, 4, negative 1, 0. And let's see, this one there's no A, so that's 0A, negative 1, 3, and 0. Going to your calculator, set up equation, we want number 2, and then enter the values. 1
equals 0 equals 0 equals 7 equals. That takes care of the first row. Negative 1 equals 4 equals negative 1 equals 0 equals 0 equals negative 1 equals 3 equals 0 equals. And if we've done it right,
voltage A is equal to 7 volts DC. We kind of already knew that, didn't we? So that's a good sign, though. Voltage B, that would be the next one, is 1.9 volts DC. And voltage C is approximately 640 millivolts DC. Just like before, we could describe nodal analysis as an algorithm. The first step is to write the Kirchhoff's current law equation for each node. I would encourage you to assume all currents leave. We do that because it makes the math easier. And once again, it's a muscle memory question. So for example, if you come up here, these here are actually B minus 0 divided by 2. Anything going to ground becomes a simple fraction, such as this. Next, we simplify. We put it into matrix form, and then it's over to the calculator. Let's end with one last example. It helps if we establish that reference node, so we'll use that point there. And then I have to ask you, how many nodes do you see? Well, we could argue that's 1, so we'll call that voltage A. There's a node there, we'll call that voltage B. And there's one here, so we'll call that voltage C. Starting with node A, again, we assume all currents are leaving the node. That gives us 2 amps because it's in the proper direction, plus, let's see, A minus B divided by 2 plus 1 is equal to 0. Simplifying that, that's A minus B is equal to minus 6. For node B, we'll assume that is leaving, and that is leaving. So this becomes B minus A divided by 2. That takes care of that one. For the 4 ohm resistor there for our R2, we would say B divided by 4. And for R3, we have B minus C divided by 3 equals 0. Simplifying that, negative 6A plus 13B minus 4C is equal to 0. And then we have node C. Our currents are in that direction, and that direction. So that would be minus 2 plus, let's see, what's this one? That would be C, right? C minus B divided by 3. And then this current right here is 3 amps. Plus 3 is equal to 0. Solving for that, C minus B is equal to negative 3. Once again, we have 3 equations with 3 unknowns. We put that into matrix form. So for node A, it is A minus B plus 0C is equal to negative 6. For node B, it's negative 6 plus 13. B minus 4C is equal to 0. And for node C, oh, I did something bad here. Let's fix this. So that's negative B plus C is equal to negative 3. There we go. That'll make this easier to enter. So it's negative 1, 1, and then 3. So there we go. That's our equations in matrix form. And now we go to the calculator. Let's go back to the beginning and do a quick review. Somewhere up here, we described mesh analysis as an algorithm. And I very much encourage you to always work these problems the same way. We start in the lower left, we move in a clockwise direction, the resistors are positive, we substitute in a voltage as a current times a resistance, simplify, matrix form, and then walk over to the calculator. We presented those ideas in this example. Again, we always start in the lower left corner and we made a loop. We made 3 loops for this particular one. 3 unknowns, 3 equations. We were able to solve that. Next, we talked about nodal analysis. This time we used current, and our muscle memory tells us to sit on a node and then assume that the current is leaving from that node, right? And all the currents leaving the node sum up to equal 0. We simplify the equations, which I would argue is a bit more complicated in nodal, only because everything turns out to be a fraction and you have to get rid of those fractions. We set this up into a matrix, and then we use the calculator again. Here was an example where we exercised all of those. We had the nodes. We were sure to establish our ground node. We referenced everything relative to it. And then again, we assumed all of the currents were leaving. Do give yourself a little bit of time to work these problems. It's challenging to get started. I'll give you that. It's not very fun. But once you get the process down, once you get through a few of these problems, that muscle memory will kick in and you can get the equations written very, very quickly.